There are probably 2 million asteroids in our solar system.
The reason that Psyche is unique is that it is metal rich.
It's believed that it may be a remnant core of an early planetesimal.
One of the ingredients that went into making our Earth, and one that we cannot see any other way. And it would be the first metal object that humankind has ever visited.
Studying the evolution of a planetary body is a detective story.
I think the only thing we know is that it's not going to look like what we think it's going to look like, and it's going to be really interesting, whatever we find.
Space is always more amazing than we can imagine with our minds.
Hello, and welcome to NASA's Kennedy Space Center on Florida's Space Coast. Thank you for tuning in for the Science News Conference for NASA's Psyche mission, humanity's first mission to visit a metal-rich asteroid. I'm Alana Johnson, Senior Communications Specialist for NASA's Planetary Science Division. We are just 2 exciting days away from a moment years in the making. NASA's sending its Psyche mission to examine a world substantially made of not rock and not ice, but of metal. Today, I'm joined by a panel of experts to give you a broad overview of Psyche's science. Lori Glaze, Director of NASA's Planetary Science Division at NASA headquarters. Lindy Elkins-Tanton, Psyche Principal Investigator, Arizona State University. Ben Weiss, Deputy Principal Investigator and Magnetometry Investigation Lead, Massachusetts Institute of Technology. David O, Chief Engineer for Operations, NASA's Jet Propulsion Laboratory, and A.B. Biswas, Project Technologist for the Deep Space Optical Communications Experiment. Thank you to the media for joining us, and we'll be taking your questions right after opening comments from our mission experts. Those of you who are watching online can submit a question at any time using the hashtag AskNASA. And now I'd like to kick it off to Lori Glaze.
Great. Thank you so much, Alana. It is just incredibly exciting to be here with everyone and with everyone online, getting ready for the launch of this incredible mission, the Psyche mission. But first, I want to provide a little bit of context for Psyche, the asteroid. There are, of course, diverse populations of asteroids across our solar system. And these remnants that are left over from the earliest times in the formation of the solar system each can tell an exciting chapter of our origin story. Within Planetary Science Division at NASA, we have almost 40 missions that are currently either in development or in operations. And of those 40, 7 of those missions are actually focused on trying to understand what asteroids can tell us about our early formation and evolution. And in fact, 4 of those missions are celebrating some important milestones this autumn. We're calling Asteroid Autumn. If I could have my first graphic, please. We kicked off Asteroid Autumn actually a couple of weeks ago out in the Utah desert when the OSIRIS-REx samples returned to Earth. That spacecraft has now been repurposed to go visit another asteroid called Apophis. We also celebrated, 2 days after that return, the 1-year anniversary of the double asteroid redirection test, where we, on purpose, impacted an asteroid with the spacecraft, the DART spacecraft, and for the first time ever, humanity was able to change the orbital trajectory of a celestial body. Now, tomorrow, those samples that we brought back from OSIRIS-REx, we are going to share the world, kind of our first look at those samples and our first impressions of what we believe we brought back from the asteroid Bennu. So that's going to be an exciting milestone tomorrow. Of course, we've got the Psyche launch coming up. I'll leave that to the team to talk about. And then coming up on November 1st is a milestone for our Lucy mission. Lucy, a mission that is going to ultimately, towards the end of the decade, explore a special category of asteroids called the Trojans that lead and trail Jupiter in its orbit around the sun. But coming up on November 1, Lucy's going to fly by a main belt asteroid called Dinkinesh. That'll allow them to do some risk reduction on the spacecraft and try out some of the terminal tracking software that they have there. It'll be a really unique opportunity for them to try out everything on the spacecraft. So with that, I really do want to make sure we have time for the whole team here to tell us about the exciting mission. Before I hand it over to the PI, Lindy Elkins-Stanton, I just want to give my thanks to the entire team. They've come through some tough times and really have done an amazing job on this mission. We know we're ready and cannot wait to get launched later this week. Thanks. Take it away, Lindy.
Thanks, Lori. Yeah, it is all about the team. It really is. We're just days away from launching a mission to an object that humankind has never before studied up close. We've visited either in person or robotically worlds made of rock and worlds made of ice and worlds made of gas, as Alana talked about. But this will be our first time visiting a world that has a metal surface. So it's primary exploration of a new kind of world. There aren't that many completely unexplored types of worlds in our solar system for us to go see. So that is what is so exciting about this. And here's the thing. We do not know what Psyche looks like. We'll show you here an artist's impression of Psyche. And we've been using this wonderful art by the artist Peter Rubin. He and I Zoomed on the weekends for about a year while I told him all the scientific hypotheses that we have about this body, motivated by meteorites, motivated by theory and models, motivated by observations. And he made them into art. But let me show you for a moment what we can really see of this asteroid. What you're going to see next is what we call a shape model. Now, this is a model that is created by Mike Shepard and his team. This is not a photograph. What this is a computer compilation of radiation that has bounced off the surface of Psyche as it spins on its axis. So they use radar from Arecibo and infrared and visible light from many different telescopes and compiled that all together in a computer to make a model of the shape. So we think we have an idea of what its shape is. And I always joke that it's shaped like a potato because potatoes come in many shapes, so I'm not wrong. But we're gonna find out when we get there what its shape really is. This is very helpful for planning the mission. And so finally, this next image is what we actually see when we look at Psyche from the Earth. And we've drawn a circle around Psyche here so that you can tell it apart from the stars that are the other light dots. And of course, the word asteroid means star-like. These are relatively small bodies far away. Although Psyche is large for an asteroid, it's about the size of Massachusetts without the Cape. Its surface area is the same as the area of California, more or less, so it's quite large that way. But even in Hubble, it's just a few pixels. So we've talked a lot in the past about the data that shows us that Psyche has to be mainly metal. It's kind of confusing to say we don't know what it looks like, we don't have a photo, but I can tell you it's made of metal. We know that its density is very high. We know the shape of the reflected light off of its surface and the way radar interacts with it. So we're quite confident that it is largely made of metal along with something else. That something else might be rock, it might be sulfur-based, it might be carbon-based. We don't know. And that is really the excitement of this. One of the things that we on the team, and in fact the whole scientific community, have been asking ourselves now for a long time is, what do we think it's going to look like? What are the scientific motivations, scientifically motivated ideas? One of the key ones is, what does a crater look like into metal? We've seen craters into rock, like on the Moon and Mars, and into ice, and of course we've seen craters on the Earth, but we've never seen craters into metal except for little tiny ones in test apparatus. One thing that happens when there's a high-speed crater is that a cup is formed and there's that spray upward. And when it's a rocky crater, that ejecta just falls down again on the outside. But sometimes with metal craters in the lab, that ejecta actually freezes before it falls. And so we think that with small craters on Psyche, there actually could be little spires or spikes, and then there would be ejected little pieces of metal that might form almost a metal sand on the surface of the body. So that's one idea that we have. We're very excited to see hopefully some large craters on Psyche as well. Another one is that way back 4,568 millions of years ago, at the beginning of our solar system when Psyche was formed, it was hot and liquid, and it might have had volcanic eruptions onto its surface. And there's a whole geochemical story behind this, which I'm not going to get into in this moment, but to say that it seems highly likely that it might have had sulfur-rich eruptions from volcanoes, or at least from fissures, when it was very, very young. So maybe today we would see the remnants of those flows on its surface. There also could be giant cliffs as it shrunk as it froze. And so would we see spiky metal craters, huge cliffs. Would we see old, eroded lava flows that would be greenish yellow from their sulfur content? This is our scientifically motivated idea. Almost certain to be completely wrong. It's going to surprise us when we get there. We're going to find out that our basic scientific understanding is going to be updated, and that's why we need to go. So that's the real excitement for me. We don't know what it's going to look like. We're going to be surprised. We're going to learn something new about a fundamental building block for rocky planets, that is their metal cores. It's as if the Earth was a cake. It had been all mixed up and heated and made into its final cake, and we don't know what the flour and the eggs and the butter are. So we're going to go meet one of those ingredients when we go see Psyche. So today, just 2 days from our first launch opportunity, I've been working on this project. Ben and I have been working on this project for 4,473 days, or 12 years. And so, so many emotions and thoughts at this moment. But one thing about the miracle that humans can do these mega projects that take thousands of people, and no single person actually understands how the whole thing works, and it lasts for decades, is that every seeming finish line, like a launch, is actually the starting line of the next marathon. And so we're really excited to see what comes next, and eventually to be at this asteroid and to share these images with the whole world so we can all look at the same time. Thanks so much for coming today and for supporting this Psyche mission. And I'm going to turn it over now to Ben Weiss, who is Psyche's Deputy Principal Investigator.
Hi, so I'm going to tell you about how we're going to use observations at the asteroid to understand how Psyche formed. And that's our mission's central science objective. So we have two leading ideas for how Psyche formed. One is that it's a core of a body, analogous to like what is inside the Earth, a molten metallic center of the Earth and other large planets. But in this case, that Psyche had its outer layers stripped off by asteroid impacts in the early solar system, so we can see its surface today. And the other idea is that Psyche is a kind of primordial unmelted body, basically formed of the very first materials in the solar system that came together under gravity and basically has been preserved in this primordial state ever since. So we are going to go into orbit around Psyche and measure its various properties at lower and lower altitudes. And we're carrying 3 different instruments. And we're also going to be using the radio antenna to look at these different ideas. And really the key characteristic of a body that's a core is that there's large regions of almost pure metal and maybe other regions that are pure rock. That's the characteristic of large-scale melting in which a core will separate out from a body. So each of the instruments is going to make an observation that looks at that metal distribution and rock distribution. But before we talk about the details, let's just show you what the spacecraft looks like. So here's the Psyche spacecraft. First, we're pointing out the X-band high-gain antenna, and then we're going to show you 2 other antennae on the bottom. These are used for communication and also for tracking the spacecraft's position. Then we've got multispectral imagers, a pair of them. And we've got the gamma ray and neutron spectrometer for measuring composition. And on the end of this other boom here, we've got 2 magnetometers for measuring the magnetic field. Okay, so let's talk about how we can use these data to understand Psyche's origin, starting with the antenna. So we use the antenna primarily for communication with the spacecraft, but it turns out you can also use this to determine the gravity field. So just like a train, when it comes towards you, it's got a higher pitch, and when it passes you, it's got a lower pitch. We can look at the pitch or frequency of the radio waves coming from the antenna and figure out how fast the spacecraft is moving. And when it's in orbit, we can track this speed as a function of its position around the asteroid. And from that, we can see how lumpy the gravity field is. So when it's above a dense region, it might be moving faster. And when it's above a less dense region, the spacecraft might be moving slower. And so if we see large regions of high gravity and low gravity, like kind of a lumpy gravity field, that would support the idea that Psyche formed as a core. Whereas if it's kind of a smooth gravity field, that would suggest the metal and rock are mixed at fine scales and it's unmelted. Okay, the second instrument is the multispectral imager. And like its name says, like we can take images in different spectra. So basically we can tell the color of the asteroid. And it turns out the metal has a very characteristic red color that we can distinguish it from minerals. And so this instrument will take the highest resolution data of the surface, and we'll be able to see, whether there are large regions of metal separated from large regions of rock. We also just are dying to see what a metal world looks like, as you heard from Lindy. And so, what does a volcano look like? What does a crack look like? What does a crater look like? What does a lava flow look like? The multispectral imager is going to be a fascinating window into metal world. Okay, the next instrument is a gamma ray and neutron spectrometer. And this is a fascinating instrument. The way it works is that Psyche is constantly bombarded by high-energy particles, cosmic rays produced by the sun and from outside the solar system. And these cosmic rays interact with the atoms inside Psyche, and those atoms will emit characteristic gamma rays, high-energy light essentially, and neutrons. And we can identify their composition essentially by looking at these gamma rays and neutrons. And so it turns out, among other things, the gamma ray neutron spectrometer is very, very sensitive to metal. So we'll be able to map the iron composition and look again for large regions of metal, see whether it's separated from rock. Okay, and then that brings us to the magnetometer. So the magnetometer is going to be trying to measure the magnetic field around Psyche. And another characteristic of planetary cores is that they often generate large-scale magnetic fields, the way the Earth's core is. When they're molten, the churning of this conducting liquid generates currents, which then produce a magnetic field. So Psyche today is long frozen, but if it formed as a metallic core in the early solar system, it was once a molten body, and it would have been cooling really quickly and potentially generating a magnetic field. Now, that magnetic field could be imprinted in the outer layers of Psyche, the cold exterior, as a kind of echo or fossil that we could then detect today. And the way this works is that this ancient magnetic field kind of acts on electrons inside the outer layers of Psyche, and they're like little compass needles because they're little spinning balls of charge, and they will align in the direction of that ancient magnetic field when it's present. But the key thing here is that even when that field is long gone, these electrons can stay aligned in the direction of that ancient field for many billions of years. We, in fact, have seen lots of evidence for this in my laboratory and others measuring the remnant magnetization of meteorites. So we can see that early asteroids seem to generate magnetic fields in this way. So what we're going to be looking for is this kind of remnant magnetic field around Psyche, like what you'd see around a bar magnet if you sprinkled little dust, iron filings on the surface of it. Okay, so that's the instrument suite. No single instrument by itself will tell us whether Psyche is a core. It's the combined data from all these different instruments. And I just want to say that this, too, for me, is a very personal moment. You know, my hair was brown when we started working on this, and you know, then it's also crazy to think about that we're kind of only halfway through this journey. And with that, I'm going to pass it over to David O, the Chief Engineer for Operations.
Thank you, Ben. I'm going to talk to you a little bit about the mission, because launch is just the start of a long and exciting journey for our spacecraft. The asteroid Psyche is where we need to go to get our science, and it's located at the outer part of the main asteroid belt between the orbits of Mars and Jupiter. It is 3 times farther from the Sun than the Earth and 2 times farther from the Sun than Mars, so we've got a very long way to go. If we can put up the first graphic. In order to get to Psyche, the spacecraft is going to travel 2.2 billion miles over the course of the next 5.9 years. And the Falcon Heavy rocket is what will lift us off the Earth and get us into space and moving away and in the right direction. But in order to accomplish the rest of the mission, we will use the spacecraft's onboard propulsion, an ultra-efficient advanced ion propulsion system. If we can put up the next chart, please. What you see here in this chart is the Hall effect thrusters that will propel us on our journey through the solar system. These thrusters use electricity to ionize xenon gas, a noble gas, and then accelerate those ions, those charged ions, through an electric field to very, very high speeds. They come out of the thruster going at 15 kilometers per second, or 9 miles per second. And that's 5 times faster than the speed of the fuel coming out of a regular chemical rocket. It's this super high speed which makes them super efficient and is what allows us to be able to use these thrusters to go all the way out to Psyche and to get into orbit around it. On the left, what you see is a picture of what the thruster looks like when it's operating in a vacuum chamber on the Earth. That blue glow that you see there is the characteristic blue glow of ionized xenon. It's the same glow that you see in xenon headlights on the Earth, because we use xenon inside of headlights on cars in some applications. But we take that plasma and we accelerate it through this this electric field in order to generate thrust. This is a solar electric propulsion system. It takes electricity from our solar rays and converts it into thrust in these rockets. So you can think of this as getting thrust from sunlight. It's the ultimate in green propulsion for our spacecraft. Now, these thrusters operate super efficiently, but also at very low thrust levels. The thrust level generated by one thruster is 250 millinewtons, which is the equivalent to the weight of these 3 quarters sitting in the palm of my hand. So that's not very much thrust at all. It's a lot less thrust than the thrust that we get out of our Falcon Heavy rocket. But these thrusters can operate over long periods of time, days, weeks, months, and this small force on the spacecraft accumulated over all that time accelerates it to the high speeds we need to be able to navigate to Mars and then out to Psyche. If we can go back to that first chart, the reason I mentioned Mars is because on our way to Psyche, we're going to use every means at our disposal, and that includes not only our propulsion system, but also a little bit of cosmic trickery, because we're going to do a Mars gravity assist on our way there. We will launch and then spend the first 3 to 4 months that we're in space checking out the spacecraft. And then we'll ignite our ion propulsion system, and we'll make our way to Mars. We'll arrive at Mars in May of 2026, and 2.5 years after launch, and we won't stop there. Instead, we'll use the gravity of Mars to do a slingshot around the planet to bend our trajectory, and then we'll restart our ion propulsion system and use that to make the rest of our journey to Psyche. When we get closer to the asteroid, we'll use our imagers to take pictures and do optical navigation, and we'll use that to navigate our way into orbit around the asteroid. And we'll arrive at the asteroid in August of 2029, which means that we'll enter our first science orbit there. That's the highest of our 4 orbits where we do our gravity science, and that allows us to both get the scientific data we need to understand Psyche's composition and allows us to get the data we need to be able to navigate to the lower orbits that we go to. The lowest orbit that we'll be in is the one that's used by our gamma-ray spectrometer. That's where we can get our elemental data of the surface of Psyche. And it's sandwiched between other orbits that allow us to get our magnetometry and our imager data and do our full science mission. The science mission will last about 26 months and will be completed in November of 2031, about 8 years after launch. So this is going to be the first mission that's going to use Hall effect thrusters in interplanetary space. And this is thrilling for me because 30 years ago, when I was a graduate student, I worked on Hall effect thrusters. At the time, it was considered an esoteric and experimental technology, and a technology of the future. It was the kind of thing that you heard about in Star Wars and Star Trek. But today, we're going to make the future real, because this will be the first mission to use Hall effect thrusters to travel between the planets. And with that, I'll turn it over to A.B. Biswas, DSOC project technologist.
Thank you, David. Deep Space Optical Communications, or DSOC, riding along with making experiment for testing, returning 10 times higher data rates from Mars distances. And this is achieved by using lasers instead of the traditional radio frequency transmitters. Future NASA missions, in particular those involving human exploration of Mars or using much higher resolution instruments, demand much higher data return rates. And that's the motivation for this DSOC technology demonstration. So DSOC will start about a month after launch, operating at a weekly cadence for about 2 years into the Psyche cruise. And during this time, we'll cover distances that represent Mars distances from Earth. So JPL developed the DSOC system, which is comprised of both a flight side and a ground side. If you can show my first slide, please. Here you see the flight transceiver integrated to the Psyche spacecraft. The laser beams exit and enter through that shiny cylinder you see there, which is a sunshade for our payload. And the payload itself is shown as an inset. It's a 22 centimeter diameter mirrored off-axis telescope that is specially designed to both receive and transmit laser beams. On the ground side, if you can show the next slide, please. On the ground side, we have 2 existing assets that have been instrumented to interact cooperatively with the space terminal in order to allow communications to happen. So at Table Mountain facility, we have a 1-meter telescope that transmits a laser beam up to the spacecraft. The spacecraft assists DSOC pointing, but DSOC has inbuilt autonomy to find that laser beam, detect it, and track it. Once it can start tracking that laser beam, it knows where to point down its laser beam, and it sends a downlink beam to the 200-inch Hale telescope at Palomar Observatory. And that's where the data is received. Both these laser beams are modulated, which means they're flashing on and off, and those flashes are timed, and the timing of those flashes is what encodes the information that's carried over these laser beams. So DSOC is NASA's first beyond the moon laser communications demonstration. In fact, it's 1,000 times beyond the moon, almost 230 million miles. So this huge increase in distance brings new challenges. Foremost among these challenges is pointing a narrow laser beam back to the ground receiving station. And this can be imagined as trying to hit a dime from a mile away while the dime is moving. And once you achieve that feat, the signal that is received is still very weak, and therefore requires very sensitive detectors and processing electronics, which can take that signal and extract the information that's encoded in it. So JPL has developed a host of new technologies, many of them flying for the first time, which are distributed both on the flight side and on the ground side. So on the flight transceiver, we have lasers that put out precisely timed laser pulses. We have sensitive cameras that detect the laser beam that comes up from Earth. And we have an assembly of sensors and actuators that help control the laser beam pointing. On the ground, we have, if we could go to the next slide, please. We have several technologies on the ground, but the most exciting one is the superconducting nanowire detector. In the next slide, please. This is a mesh of nanowires that forms a detector that sits behind the Hale telescope. And the flashes of light that are transmitted from space, they get weaker and weaker in strength as they approach Earth. And by the time they get to Earth, they are just a handful of photons or quanta of light energy. And as these photons hit this detector, which is at about 1 Kelvin, which is very cold, these nanowires transition in and out of superconducting state. And as they do that, each time they make a transition, electrical pulse comes out. And this electrical pulse both tags the time of arrival of the photon and detects the photon. And then there's high-speed electronics that processes this and can then extract the information that's being sent over this laser beam. So here we are 2 days from launch. I think we've spent as many millions of hours as the distance that we're trying to transmit photons over. And there's been a lot of, it's a time for reflection and recognition of the hard dedication that's been from multiple disciplines. And we're very excited and eagerly awaiting validating this technology that will augment NASA's future missions. And with that, I'd like to hand it over to Alana.
Thank you, A.B. Thank you to all of our experts. The phone line is now open for those of you calling in. Please identify yourself and your outlet and the expert to whom you would like to address your question. We're going to start out today in the room. I'm going to go with somebody over here. Any questions in the room on the right side, left side, right side? Let's go right side.
Hey, Ken Kramer, Space Up Close. Congratulations first. It was wonderful to see your probe in the clean room a few weeks ago. So with all these science instruments, I wonder if you could tell us how quickly will you be able to determine it really is a metallic asteroid? Thanks.
All right, so that's this has been one of the really fascinating challenges of this project from a scientific point of view. How do you plan a scientific investigation for an object where you don't know exactly what that object is? If you knew you were going to Mars, you know when you're going to be able to see a rock. The problem with promising a time that we're going to identify some aspect of Psyche is that it's going to depend on what Psyche really is. And so there's not really a precise answer that I can give you. It might take us a little while. And one of the ways that we've organized this investigation is that all of our broad science questions require data from all of the instruments to answer. And so for ultimate answers, we're really going to have to wait till the final closest orbit when we get the gamma ray and neutron spectrometer data. There could be earlier surprises, but it's going to be a little bit of a waiting game.
I can just add one thing to that. So as a perfect example of what she just said, Psyche could be a core, but it may or may not have a magnetic field. It could be completely non-magnetic, or one of the most magnetic things a spacecraft has encountered. And if we do see that it's got a strong magnetic field, that would indicate that it formed as a core, but we might not know that until one of the lower orbits. But if it turns out it's not magnetic, then that still allows it to have been a core, but maybe it just didn't generate a magnetic field. So that's a perfect example of how we can't plan this.
Okay, we're going to go to the phone lines next. Bill Harwood from CBS is the first on the line.
Yeah, thanks very much. I think this one's for David, if I could. It's kind of a nuts and bolts question. Can you walk us through the 4 planned orbits in terms of their inclination? I got confused by the sequence and wanted to keep the altitudes and inclinations straight as you move from, the A orbit and then ultimately back out to, I guess, C. Thanks.
Let's see. You guys correct me if I have it's AB1, C. Then D. Okay, so we start in the highest orbit, right, which we call, so first of all, we have 4 orbits, and they're named very originally orbit A, B, C, and D, right? But we actually will go from orbit A down through B, C, and D, and then we will come back up to orbit B at the end of the mission. So as we go through those orbits, we're basically, A is the highest altitude, D is the lowest altitude. D also, I believe, has an inclination change associated with it at the low altitude to be able to get the science. So we go A, well, I guess it's very simple, A, B, or B1 if you want to call it that. We skip C on the way down. Okay, so let me say it like this. The order is we do orbit A, then we do orbit what we call B1, then we go to orbit D, and then we come up to orbit C, and then we come up to orbit B. So that's the order in which we do it.
Okay, we'll come back to the room here in the front row, please.
Scott Bordeaux, Arizona State University. Lindy, you said in your remarks that we're almost certain to be completely wrong. We don't know what it's going to look like. If it isn't what you expect, what could it be?
So much fun to be asking this question to scientists all over the world. As I've been giving talks for the last 10 years, I always ask them, what do you think it could be? Did my sound just go off, I think? Is it okay? Okay. And so we had one very serious person stand up once and say, well, it's not the Death Star because it's too small, and it's not the Death Star prototype because it's too big. But on a serious note, it could be the part of a metal core, which is our top hypothesis. Our second most favorite scientific idea is that it could be material that formed very near to the sun and was reduced. That is to say, the oxygen atoms were stripped from the iron atoms so that the iron atoms became metal. This is a kind of material that's been hypothesized by planetary scientists for a long time, but we haven't actually found any before. And so think about what this means. When there's only one object like Psyche in the whole solar system, we're not talking about a normal distribution of processes and we choose the most common. It's something unusual. It's something that doesn't happen often. And so I think there's a very good chance that it's going to be outside of our imaginings, and that is my fondest hope.
Okay, we're going to hop to another phone line question from Jim Siegel of NASA Tech on the line. Go ahead, Jim.
Hi, everybody, and thank you for taking my question. I'm curious about how many other asteroids of all those that you've mentioned out there. There's 2 million, I guess. How many others do you suspect are mostly metal? And how was this asteroid specifically chosen for this mission? Thank you.
Do you want to do this, Ben? Sure.
Yeah, so different asteroids, we know different amounts about their mass and how big they are, so there's some uncertainties on exactly how dense various asteroids are. So depending on how you count that, maybe there's a dozen other ones that are in the range that we think might be iron-rich, and some of them are, very close to the Earth, and very small, say like a half a mile wide, and other ones in the asteroid belt. We also have, Mercury, which is not obviously an asteroid, but we think it's mostly a core. It's like 82% of its radius that's made out of metal, and there's a little bit of rock pasted on top. And we even have now, and we didn't know about this when we started thinking about this mission way back when, 12 years ago, a population of planets outside the solar system that look like they're mostly made out of metal, so-called exoplanets with sizes up to bigger than the Earth. So there's a huge diversity, it turns out, despite Psyche being an example of one. It's also kind of representative of a diverse range of bodies that we think are maybe metal worlds. And what was the second part of your question? Did I get your question correctly?
Asteroid to go to of
right.
all of them that might.
Right. So Psyche has, for at least a few decades, has been something that people wondered about. They knew about its density, and it's been a kind of terra incognita and a place of excitement where everyone could speculate about what a new body would be like that's so dense. And so when we came to this mission planning about 12 years ago, it was one of the first bodies we just started thinking about how cool it would be to actually go there. But the story behind ending up choosing Psyche is that we had, Lindy and I and a few others, and Maria Zuber had written a paper talking about how we could learn about the early history of asteroid geology and formation by looking at bodies that underwent large-scale melting and understanding how, in a way, how asteroids can be like little planets with core, mantles, and crusts. And so when we wrote this paper, JPL read the paper and invited us to come out to talk about how we might test these ideas. And we started working with the engineers at JPL to look at what asteroids we might be able to visit given the trajectory constraints. And like I said, Psyche was always one of those that right in the beginning attracted us, and we ultimately realized that it was an achievable mission.
Okay, excuse me. We're going to go to the phone. Alexandra Witzy with Nature.
Yes, hi. I know we're talking about science today, but with the first launch opportunity coming up and a 20% favorable weather forecast for Friday's attempt, for those of us sort of trying to juggle travel plans, what do we know about launch opportunities after Thursday? How quickly can you recycle, and what does the weather look like in the successive days?
Who wants to take that one?
Should we give it to David?
Can take that, David?
Let's see. I think I looked at the weather forecast this morning. It did look challenging for Thursday. I think we were showing maybe a 80% chance of rain and thunderstorms and things like that. The conditions do start looking better over the weekend, but I think we're still 50-50 according to the weather forecast going out. Now, we are at planetary launch, and we're aiming for a planetary launch window. We have a limited number of opportunities to go, so I think we may be pretty aggressive in our attempt to get off the ground here, but the weather will need to cooperate for us to do it.
Well, just to add, we have an opportunity every single day, and so there's actually not a huge risk here. We've got enough days, and we have a chance every single day, and so it might not be Thursday, but it's going to be really soon.
Okay, let's come back into the room right here.
Stephen Clark from Ars Technica. This is probably for Lindy or Ben, but is there any plan to look at Psyche with Webb if you haven't already, and would any Webb observations kind of give you any hints about what's to come?
Yeah, actually, I'm excited to tell you that Webb's already looked at Psyche. We got time in Cycle 1. This is a project led by a very talented young astrophysicist, Stephanie Jarmack, and I'm kind of tagging along on that team. And did not look at Psyche with cameras, though, looked at it with infrared spectrometers to see if we could see any sign of certain kinds of composition on the surface. And that data is still in analysis and nothing that can really be announced with any surety right now, but that is helping us in our story.
Okay, let's stay in the room here. Any questions from the back? No? Okay, we'll go to the phone lines. Bradley Warren with NASA Spaceflight is on the line. Go ahead, Bradley.
Hi, hey, good morning here with NASA Spaceflight. Thanks for taking my question, and just congratulations to all the Psyche teams for getting to this point. Very exciting. My question is, how soon after launch will Psyche's instruments be turned on, and what does the process for getting those instruments active look like? And then during the coast phase, will teams use the instruments during the gravity-assisted Mars as sort of like a dress rehearsal for the instruments to ensure that they're working properly and ready for use at Psyche? Thank you.
that David for ICO?
I'll start with talking about the instruments being turned on. The first of the instruments, the magnetometer, gets turned on right after we launch. 5 days after we launch is the plan, if everything's going nominally, as we say. The gamma ray spectrometer gets turned on a few weeks after that, and we'll be checking out the imagers as well during that first 4 months of operations. Maybe I'll throw it back to one of you to talk about what we do with these instruments when we go by Mars.
Yeah, it's going to be calibration, so no science, but lots of practice.
And when we turn the magnetometer on right after launch, the reason we're doing that is the magnetometer is extremely sensitive, and it turns out our main noise source is not any noise inside the instrument, but actually the magnetic field coming from the spacecraft itself. Now, Psyche, JPL did a really deep dive to try to make the spacecraft as non-magnetic as possible, and it's the field at the magnetometers is less from the spacecraft than in my 3-layer magnetically shielded room at MIT, where I make extremely high sensitivity magnetic field measurements. So they did a fantastic job. Even so, the field is not zero, and so one of the things we're going to be doing is just watching the different parts of the spacecraft as they turn on, and basically recording their signals so we can remove that from the measurements when we get at the asteroid.
Okay.
I guess I'll add the radio science, of course, is our radio system, and it'll be on 5 minutes after separation, because it's the same radio system we use to verify that the spacecraft is safe and sound.
Yep.
Okay. We're going to head back to the phones with Bill Harwood again from CBS. Go ahead, Bill.
Hey, thank you very much. I didn't state my first question very well. Let me try that again. When you guys get down to orbit D, is that essentially equatorial, and what is the science that you're doing that for specifically? I mean, I'm assuming it's gravity science and stuff like that, but can you just talk about, why you changed planes in this mission from a science perspective? Thanks.
Yeah, okay, great. The lowest orbit is very important because of the needs of the gamma ray spectrometer. All the other instruments, the neutron spectrometer, the imagers, the magnetometers, and of course the radio science, they're going to be on all the time. But the gamma ray spectrometer needs to be as close to the body as possible. And so that's why that special orbit, so that we can get the surface composition for that from that instrument.
Okay, we're going to go to Stephanie on X is asking, what cameras are aboard Psyche? Will we see any pictures along the way, like during the gravity assists?
Anybody want to take that one? I can, yeah, go ahead.
Well, so these are what we call multispectral imagers. So they take basically images in different wavelength bands. So you can basically build up kind of a color, pseudo-color map of the asteroid. And as these images are taken, they're basically going to be posted online essentially right away. So we'll all be basically seeing these images together for the first time.
Okay. We'll come back to Stephen Clark here in the room.
Hi, thanks for taking another question. I think this is probably for David. Can you kind of walk through what happens after the spacecraft deploys from Falcon Heavy in terms of deployments of appendages and first acquisition of signal, et cetera?
Sure, I can walk you through a little bit of that. The spacecraft will come off the Falcon Heavy vehicle, and then 5 minutes after it separates, it'll turn on its radio. It will stabilize itself from any spin or change in attitude that's left from the launch vehicle, and then it will deploy its solar arrays, those 2 big 5-panel arrays that come out the side. It does all of that autonomously. It does that under its own control. And then once it has deployed the solar arrays, it will find the sun and then turn itself towards the sun to get power, and then orient its antenna towards Earth so that we can get communications on the ground. We may have communications during parts of that sequence, just as the spacecraft is turning, but it's only at the very end of the sequence that we have guaranteed communication from the spacecraft. So the spacecraft largely takes care of itself upon separation if things go well. It will autonomously deploy its solar arrays, autonomously get itself power positive, get itself electrically charging its batteries, and then autonomously get itself pointed at the Earth so we can communicate with it. And that's the point at which we'll have the ground team pick it up.
And when is that acquisition nominally, the guaranteed time?
The nominal time is probably 2 hours after launch. It could be earlier because we're very close to Earth and our antennas have a very wide coverage range. So it may be that even if we happen to to turn the spacecraft through the edge of the antenna. We'll get a little coverage earlier on. It could take later in the event of contingencies on board the spacecraft, but you can call it nominally the 2-hour time frame.
Okay, we're going to go to Paru on YouTube is asking, is there a plan to bring a sample from Psyche just like Bennu? And also, can you explain what never-before-seen aspects we can get to know by studying this asteroid?
Yeah, I'm happy to take that. Yeah, no, we're not bringing back a sample. Bennu is a very near-Earth asteroid, and Psyche is a very far-away asteroid. Even at its very closest, it's 250 million kilometers away from the Earth, which is 3 times farther than Mars is at its closest. And when it's far away, it's 650 million kilometers away. So going all the way there, taking something and bring it back. Also, because we don't know what its surface looks like, we're not ready to land. We're not ready to sample. We've got to have some sense of what this object is like before we can take that next step. And so the highest level, never before explored answer is we're trying to understand about the metal core of the Earth and also Mercury and Venus and Mars, and also the Moon has a little metal core. We are never ever going to go to those cores, way too hot, way too deep, but they're central to what makes a rocky planet and also to what makes a rocky planet habitable. So this is our one way to see a core. So we say, you know, tongue-in-cheek, that we're going to outer space to explore inner space.
Okay, we'll go back to the phone lines. Will Robinson Smith from Spaceflight Now, you're on the line. Go ahead, Will.
Yeah, thanks for taking my question, and apologies in advance for the background noise. I'm making my way through O'Hare Airport. Question about the life of the Psyche spacecraft after the nominal mission completes. Assuming the spacecraft is still healthy, what additional science objectives could be added on to, and what's the plan after the planned mission? Thanks.
So why don't I take a little bit of that question, then I'll toss it to Lindy if she wants to add to it. But you know, NASA has a process by which we assess our missions after they've completed their primary operations. We actually require all of the missions to go through what we call a senior review process. And so whenever Psyche has gotten close to completing their nominal 26-month mission, we will include Psyche as part of that senior review process. They can submit a proposal. I presume that proposal will include lots of great new science that could be done through an extended mission, and it'll build on what is learned as part of the primary mission. And you've heard Lindy and the team say several times, we don't really know what we're going to find, but we know it's going to be a surprise. And so based on those surprises, I'm sure new hypotheses will come forward. And so those ideas and that new science would be evaluated as part of the senior review process. The other part of senior review is looking at the resources still available on the spacecraft, the health of the spacecraft, how is it still operating, are the instruments still functioning as they would need to do the science, and is there enough fuel and other resources on board. So we do have that process in place, so you can look forward to that senior review sometime in the early 2030s.
Nothing to add, that's it. Yeah.
Okay, I want to make sure we're covering the room here. Okay, Ken over here.
Thanks for another question. Let me ask David maybe. Are you going to plan to take any pictures of the Earth or the Earth-Moon system on the way out?
I don't think we currently have those in our plan. So I think the simple answer is no, not at this time.
Maybe I could ask one other question. I was also interested about the other metallic asteroids. Is Psyche the only one that you could have reached, or was there another one or two that you might have been able to get to with the Falcon Heavy, and how you selected between them?
Yeah,
Thanks.
yeah, we could have gotten to other ones, but Psyche is by far the largest. And the one that's most likely to tell us the most about cores. Is there anything you want to add to that, Ben?
Yeah, I would just say one of the reasons size matters here is that when you're big, you're basically less likely to be broken up and modified by impacts that hit your surface. So the largest asteroids that are bigger than 100 kilometers in radius or so, they on average, their lifetime up against being destroyed by being hit by other asteroids is longer than the age of the solar system. So going to a large asteroid is really important if you want to look at something that has a good chance of having its original structure intact, rather than being a kind of pulverized pile of rubble, like you see, for example, for Ryugu or Bennu, where they're very small asteroids, and that's why they were good targets for sampling. So in this case, we have a big body that's likely to be intact from the early solar system, or at least to have a good chance of being so.
Okay, I have a really fun question here. Manos on YouTube says, "Hello, I'm a 13-year-old kid from Greece, and I have a question. How will you reach 16 Psyche with so much accuracy? Hardware, software, technology?"
Go ahead.
Take that one?
Yeah.
It's a challenge. We have astronavigators. We have people who navigate our spacecraft, largely using the radio system that we have. We can use this combination of Doppler and what we call ranging to get very accurate readings of where the spacecraft is in space when we communicate with that. We put that into models that we have of the solar system and of the gravity of all the different bodies in the solar system. We combine that with models that we have of the thruster, and then we optimize that mathematically to develop an optimal trajectory so we can fire our thruster continually as we go and replan as we go to get us to Psyche. We do optical navigation at the end, as I said earlier, with our cameras looking at the asteroid to localize in. It's a very, very precise exercise, and it's quite a bit of mathematical effort which goes into pulling all these numbers together to make it work. But the navigators are extraordinarily good at it, as they've demonstrated to us multiple times. And I'm certainly looking forward to working with them. It's an extraordinary set of tools that they have to pull it all together and get us there.
Okay, let's come back into the room.
Forgive a stupid question, just born out of curiosity. How do you approximate conditions in space and know that this new technology will work in space?
Okay. That's a great question, right? Because the mantra that we use at JPL and throughout the industry is we test like you fly and you fly like you test. So these thrusters that we have, first of all, have been operated in Earth orbit before. So we have some evidence from space that they work. Before we put them into space, we operate them in vacuum chambers here on the Earth. We put them through thermal vacuum testing, where we heat them up and we cool them down. We put them through vibration testing and shock testing to simulate the challenges of being on the launch vehicle through launch. We do all of that work, and then we use the data that we get from those tests to estimate how we'll operate in space. Our vacuum chambers on Earth are pretty good, but for thrusters like this, they're not perfect. So we do have to do a certain amount of scaling and analysis in order to verify that the results we have on Earth are going to apply in space. So this is the first time we're flying in interplanetary space. There will be some new things that we can learn that we haven't been able to learn in Earth orbit. So we do that through this combination of testing, analysis, and then we get to space and take care of the rest, the little bit that's left in our initial testing in space.
Okay, and speaking of new things, AB, do you want to talk about DSOC a little bit?
Yeah, it's pretty much what David said. I mean, we did the same thing with all our assemblies. At the unit level, we put them through thermal vac, vibe, shake, shock, all those things. And we also did some at the assembly level, and then at the spacecraft level. So it was tested like 3 times, and then after each test, the functionality is checked, and that gives us the confidence that it'll actually work in space.
Okay, let's go back to the phone. Jim Siegel from NASA Tech is on the line.
Hi, thanks for taking my other question here. You showed a slide earlier of the route of the spacecraft with the various orbits. And I was wondering, are you going to be monitoring the route of this spacecraft in terms of its accuracy, and if it's getting off track a bit, can you modify and get it back on track? And how do you do that? Are there thrusters inside the spacecraft or what? Thank you.
I'll take that one. Yes, we do monitor the position of the spacecraft and its speed continuously as it flies. The thrusters that we have on board can be both turned in space to different directions and have gimbals on board, which allow us to steer them. And by taking a look at the data we have from the trajectory and replanning our path as we go, we can steer the thrusters to keep us on course as we go past Mars and as we get to Psyche. So it's a continuous improvement process, a continuous monitoring and optimization process as we fly.
Okay, that's all the time we have for today. Thank you to the media for all of your questions, and thank you to our panel of experts. Please join us tomorrow at 1 p.m. Eastern for the Psyche pre-launch briefing. You can find our full Psyche programming lineup and mission updates at nasa.gov/Psyche. And keep the conversation going on social media using the hashtag Mission to Psyche. And be sure to set your alarms for Thursday morning to watch our live coverage of the Psyche launch October 12th at 10:30 a.m. And we just thank you and goodbye from NASA's Kennedy Space Center. Go NASA, go Falcon Heavy, and go Psyche.